Hello, everyone. First of all, I would like to express my gratitude to Professor Tsoutos and Christos for giving me the opportunity to be here today and present my work. As mentioned in the previous lecture, Professor Tsoutos introduced the hydrolysis process, while Christos presented the life cycle assessment approach. So, building on this background, today's presentation focuses on a case study of bioethanol production from marine macroalgae, examining its environmental performance and optimization strategies. Today, we will explore how marine macroalgae can be used as a sustainable feedstock for bioethanol production, how different processing scenarios affect environmental performance, and how renewable energy integration can further improve the sustainability of the process. So, our presentation is divided into 5 main sections. First, I'll introduce marine macroalgae and explain why they are attracting attention as a biofuel feedstock. Then I'll present the process study and the different pretreatment and hydrolysis scenarios that were evaluated. Next, we will examine the environmental impacts of the optimal scenario using LCA. After that, I'll discuss optimization strategies based on renewable energy integration. And finally, I'll summarize the key conclusions and possible future improvements. So, why macroalgae and bioethanol matter? To understand the importance of this research, we first need to look at the broader context. The world is facing increasing energy demands while simultaneously trying to reduce greenhouse gas emissions and dependence on fossil fuels. Biofuels are considered one of the most promising alternatives because they can be produced from renewable biological resources. However, not all biomass sources are equally sustainable. This has led researchers to investigate new feedstocks that do not compete with food production and require fewer natural resources. One such feedstock is marine macroalgae. So, the main biofuels currently used are bioethanol, biodiesel, biomethane, and pellets. In this presentation, our focus will be on bioethanol. The bioethanol investigated in this study is produced from third-generation biomass, specifically marine macroalgae. In general, biomass feedstocks can be classified in 3 main generations. First-generation biomass includes food and agricultural crops, such as corn and sugarcane. Although these feedstocks can produce bioethanol efficiently, they often compete with food production and agricultural land use. Second-generation biomass consists of lignocellulosic materials, including agricultural and forestry residue. These materials reduce competition with food crops, but usually require more intensive pretreatment due to their lignin content. Finally, third-generation biomass includes aquatic biomass, particularly microalgae and macroalgae. These feedstocks have attracted significant interest because they grow rapidly, do not require fertile agricultural lands or freshwater resources, and contain high amounts of carbohydrates that can be converted into bioethanol. For these reasons, marine macroalgae are considered a promising and sustainable feedstock for future bioethanol production. As mentioned previously, macroalgae are not only useful for energy production, they can also be used in food products, cosmetics, pharmaceuticals, fertilizers, and various industrial applications. So this versatility makes algae an important component of the emerging bioeconomy, and the possibility of producing both energy and valuable co-products increases their economic attractiveness. Now that we have seen why macroalgae are considered a promising feedstock for bioethanol production, let's take a closer look at the different types of algae. Marine macroalgae are generally classified into 3 main groups: red macroalgae, green macroalgae, and brown macroalgae, scientifically known as Rhodophyta, Chlorophyta, and Phaeophyta, respectively. Although all 3 groups can be used as biomass resources, they differ significantly in their biochemical composition and carbohydrate content. These differences are important because they influence the convention process and ultimately affect bioethanol production efficiency. In the next slides, we will briefly examine the main characteristics of each group and some representative species. Red macroalgae are rich in agar and carrageenan, and are widely used in food and pharmaceutical industries. Common examples include species like Porphyra, Gracilaria, and Gelidium. Green macroalgae now, or Chlorophyta, contain cellulose and ulvan as their main polysaccharides. Typical examples are ulva, cladophora, and caulerpa. Brown macroalgae, or Phyophyta, contain laminarin and mannitol and include species such as laminaria and sargassum. The different carbohydrate compositions influence sugar release and ethanol yields during processing. As with just in brown macroalgae like sargassum, are chemically characterized by unique polymers like laminarin and mannitol. But these structural properties doesn't just exist in a vacuum or a controlled farm. They have major ecological implications right here in the region. When we transition from general classifications to look specifically at the Mediterranean basin, we found that some of these exact groups are behaving aggressively. This brings us to a critical aspect of our feedstock selection, the reality of opportunistic blooms and invasive species. Let's look at how this environmental threat can actually be reframed into a major circular resource for our bioethanol system. An interesting aspect of Mediterranean macroalgae is that some species are considered invasive and can negatively affect local ecosystems. Species such as Caulerpa cylindreichia, sorry for my pronunciation, has spread extensively throughout the Mediterranean basin. So the management of these blooms often requires biomass removal. So instead of treating this biomass as waste, it could potentially be utilized for biofuel production, creating an opportunity to combine environmental management with renewable energy generation. Now let's look at the raw material itself. Why choose marine macroalgae over traditional land-based biomass? These are 5 core advantages presented here. First, resource protection. Unlike first-generation biofuels, macroalgae require zero agricultural lands and zero fresh water. This completely eliminates competition with food crops. Second, we have structural efficiency. Terrestrial plants contain lignin, which requires massive energy and harsh chemicals to break down. Macroalgae have virtually no lignin, which drastically simplifies our pretreatment phase. Third, we have high yield potential. Macroalgae are carbohydrate-rich factories containing 40 to 70% carbohydrates by dry weight, providing a massive amount of fermentable sugars. Fourth, biological performance. They feature rapid growth rates and exceptional bioproductivity, often growing multiple times faster than land plants. Finally, scalable cultivation. With our oceans covering most of the planet, we have vast potential for large-scale marine farming without any geographical land constraints. However, while the biology gives us a great head start, processing this wet biomass takes a lot of energy. With those raw material benefits in mind, let's examine how we actually transform this biomass into fuel. The product of bioethanol systematically moves through these foundational stages. All right. It begins with harvesting, followed by mechanical pretreatments, meaning drying and grinding. Next is chemical pretreatment phase, which disrupts the cell wall and breaks down the complex polysaccharide structures. This creates a substrate ready for the hydrolysis stage, where these polysaccharides are further broken down into fermentable monosaccharides. We then move to fermentation, where these sugars are converted into ethanol using yeast, such as Saccharomyces cerevisiae or common dry yeast. Finally, the process concludes with distillation and dehydration, recovering ethanol at a purity of 95% and 99.5% respectively. The main objective of this study is the comparative life cycle assessment of three distinct production scenarios, which differentiates in their method of pretreatment and hydrolysis. Sorry for a moment. Okay. So we have scenario 1 that utilizes acid pretreatment combined with acid hydrolysis. Scenario 2 pairs acid pretreatment with enzymatic hydrolysis. And at scenario 3, that combines alkaline pretreatment and enzymatic hydrolysis. At the end of the entire process, specifically after the dehydration stage, a final quantity of bioethanol was produced for each scenario. As you can see from the data, scenario 2 achieved the highest yield, producing the largest quantity of bioethanol with 262.4 kilos bioethanol, which is our ultimate target. At this point, I want to add that to quantify the environmental footprints of this pathway, the evaluation was performed using CIMAPRO software, applying the recipe 2016 midpoint method based on the World 2010 baseline. However, this leaves us with a critical question. Is scenario 2, which produces the maximum amount of bioethanol, also the most environmentally friendly option? To answer this, we must look at the actual environmental scores. So we analyzed various factors impacting both the environment and human health. Across all scenarios and process stages, the results revealed that terrestrial ecotoxicity is consistently the dominant environmental burden. When we compare the pathways, we notice that scenario 3 systematically exhibits the highest environmental impacts across the key stages of the process. This gap becomes particularly visible during the thermal stages, specifically distillation and dehydration, where the differences between the scenarios expand significantly. To give you an idea of the scale, scenario 3 presents a roughly a 30 to 40% higher burden than scenario 2, and about a 35 to 45% higher burden compared to scenario 1. In sharp contrast, scenario 2 demonstrates the lowest environmental impact values overall throughout the entire production chain. Therefore, because scenario 2 combines the lowest environmental footprint and with the highest bioethanol yield, it clearly emerges as our environmentally optimal solution. This brings us to section 3 of the study. And now that we have isolated our baseline optimal scenario, we will conduct a targeted environmental impact assessment to break down its internal processing stages. Let's examine exactly where the primary material and energy burdens are concentrated within this pathway. Since terrestrial ecotoxicity was identified as our dominant environmental impact, we performed a detailed contribution analysis specifically for scenario 2. As you can see from the results, the primary source of environmental burden is low voltage electricity. If we dig deeper into the life cycle of this energy, the most significant factor is the production of high voltage energy from oil. This is a critical finding because it directly relates to the release of heavy metals during the oil combustion process, which leads to high soil toxicity levels. Now, to ensure the reliability of our findings, we conducted a Monte Carlo uncertainty analysis for the optimal scenario 2. This allows us to see how sensitive our results are to data variations. Looking at the coefficient of variation, CV, for the pretreatment stage, the CV was 15.8%, which indicates good stability and consistency in our results. However, for the hydrolysis stage, the CV increases to 27.1%. This higher fluctuation is primarily attributed to the high sensitivity of enzymes to operation parameters such as pH, temperature, and dosage. We also observed high variability in specific impact categories. In freshwater eutrophication, the uncertainty is mainly driven by phosphorus emissions, because even minor fluctuations in these quantities can lead to significant differences in the final result. The category shows high sensitivity. Finally, for the category of human non-carcinogenic toxicity, is heavily influenced by the heavy metals associated with electricity and chemical production. Because these specific emission datasets inherently carry higher levels of uncertainty, they impact the overall variance of this category. Moving now from our statistical validation, we now enter the most critical part of the study, optimization. Since we identified fossil fuel-based energy as our primary environmental bottleneck, we developed 3 intervention strategies to mitigate these impacts. In the first scenario, we focused on the electrical demands, so we modeled the replacement of 50% of the grid electricity with an on-site photovoltaic system. This is a 557 kilowatt peak system utilizing polycrystalline silicon technology. Now, in the second scenario, we addressed the thermal demand. As we noted, distillation is extremely heat intensive, so we proposed replacing 35% of the natural gas generated heat with solar thermal collectors, specifically using flat plate copper technology. As far as scenario 3 is concerned, it is our most ambitious model, a hybrid integration of both photovoltaic and solar thermal systems. In this case, we cover 50% of the electricity and 35% of the thermal energy through renewables. Now, before we analyze the results of these optimizations, we must establish the boundary conditions and assumptions of our model. In any LCA, transparency regarding data constraints is vital for a correct interpretation of the results. First, regarding system demand, we have treated the total electrical and thermal demand as a constant. This means our study focuses exclusively on their impact of shifting the energy source without assuming any changes in process efficiency or consumption behavior. For the hybrid configuration, we model a balanced hybrid approach, meaning for electricity, we assume the 50-50 split between the photovoltaic system and the national grid. And for thermal energy, we aimed for a 35% solar contribution, with the remaining 65% supplemented by natural gas. However, we must acknowledge certain data proxies. Due to the lack of specific industrial time series data for Greece, we utilized photovoltaic generation profiles from Spain as a climatic proxy. Furthermore, in the absence of a dedicated industrial dataset for heat production, we employed the multiple dwelling model to approximate centralized thermal energy generation. Finally, for the sake of model clarity, this current iteration excludes seasonality effects, energy storage requirements, and operation of system losses. With our boundary conditions established, let's look at the quantitative performance of our 3 strategies across the key impact categories. First, regarding global warming potential, optimization 3 has the most significant results. Compared to our baseline, we see a substantial 28% reduction in global warming Optimization 1 now, focusing on photovoltaics, follows closely with a 24% reduction. In contrast, optimization scenario 2, the solar thermal focus, shows a negligible improvement of only about 4%. Similarly, looking at fossil resource scarcity category, we see a matching trend, meaning that optimization 3 leads with a 29% reduction in source depletion, followed by optimization 1 at roughly 24%, while optimization 2 at roughly 5% improvement. Therefore, we can conclude that for both global warming and fossil resource scarcity, the hybrid approach of the optimization 3 is clearly the ideal solution. However, when we turn to terrestrial ecotoxicity, the hierarchy changes completely. Here, optimization 1 achieves the most significant decrease, reducing the environmental burden by 8 to 9% just by implementing the photovoltaic system. Optimization 3 scenario follows with a smaller 5 to 6 reduction, while optimization 2 actually increases the burden by about 2%. So this shows us that adding solar thermal collectors introduces material-driven toxicity that offsets some of our gains. To fully understand these shifts, we will now look at the detailed contribution analysis for each optimization scenario. And this will allow us to isolate and identify exactly which processes and materials contribute the most to terrestrial ecotoxicity across all three models. Now, let's look at the detailed contribution analysis for our first two optimization strategies. Please keep in mind that the data displayed in these tables focuses specifically on the distillation stage, as this is the unit operation with the highest energy demand in our entire process. If you look at the top table for optimization scenario 1, where we integrated the photovoltaic system, a clear paradox emerges. Earlier, we saw that this scenario gives a better reduction in terrestrial ecotoxicity than the hybrid model. However, if we look at the highlighted hotspots, this ecotoxicity footprint is directly linked to the environmental impacts of manufacturing the photovoltaic system equipment, specifically the extraction and processing of raw metals. The data reveals that the main contribution to terrestrial ecotoxicity comes from the production of the polycrystalline silicon solar cells, as well as the background low voltage electricity used during the manufacturing phase, of course. Therefore, while PV cells drastically improve our carbon footprints, our heavy reliance on raw materials and metallic resources places a strict limit on how much we can reduce soil ecotoxicity. Now, if we look at the lower table for optimization scenario 2, which focused on solar thermal energy, the structural limitations of a partial energy shift becomes very obvious. Our analysis shows that the dominant environmental burden in this scenario is still heavily related to low voltage electricity, and specifically in the production of high voltage electricity from oil. This proves that a thermal intervention alone is simply not enough for a meaningful environmental improvement. Consequently, while the solar collectors successfully reduce the impacts and resource depletion associated with natural gas consumption, their overall effect on the total life cycle remains limited because the distillation stages have heavy electrical demands that are left untouched. Moving on to the optimization scenario 3, our hybrid model, we observe a combination of both behavioral patterns on a single chart. This scenario manages to strike a balance by dramatically lowering our dependency on fossil fuels, but it simultaneously accumulates the material footprints of both interventions. As highlighted here, the main contribution to terrestrial ecotoxicity continues to come from the production of the polycrystalline silicon solar cells. So this brings us to a fundamental takeaway in that life cycle assessment theory that perfectly encapsulates everything we see on these last two slides, that renewable energy technologies are not environmentally neutral. They successfully eliminate operational impacts, such as burning fossil fuels or consuming natural gas, but they systematically shift a portion of these environmental burdens to other categories, such as the material heavy toxicity of equipment manufacturing, mining, and metal refining. This brings us to the final section of the study, our key conclusions and improvement strategies. Looking at the overall evaluation of this marine biorefinery system, we can summarize our core findings into 5 key points. First, the environmentally optimal scenario is scenario 2, which combines acid pretreatment with enzymatic hydrolysis. As we demonstrated during the initial staging analysis, this process pathway achieves the highest bioethanol yield while minimizing net environmental damage. Second, regardless of the scenario or optimization layer analyzed, terrestrial ecotoxicity is consistently the dominant impact category across the entire life cycle. This is an essential hotspot to track as it highlights how background industrial inputs affect soil systems. Third, regarding our optimization efforts, the integration of renewable energy sources smooths out environmental impacts, but at the same time burdens other categories. Fourth, we must recognize that beyond pretreatment hydrolysis, distillation and dehydration determine the footprint. Because these final purification stages consume the vast majority of the plant's thermal and electrical energy, any process modification must target these operations to make a significant difference. Ultimately, this proves our final point. Sustainability requires energy optimization of the process as a whole. We cannot evaluate a biofuel simply by looking at the biology of the feedstock or the chemistry of the reactor. We must optimize the entire background and foreground life cycle together. With these conclusions established, let us look at the concrete future studies we propose to achieve this whole process optimization. To further reduce now the overall environmental footprint, our focus must extend beyond the baseline configuration. First, we require strict thermal integration across the entire process, alongside the targeted reduction in the energy demands of our separation stages, such as distillation and dehydration. Second, we must incorporate circular management practices, specifically addressing the end of life and manufacturing impacts of our renewable energy equipment. Additionally, implementing water reuse strategies and investigating alternative low energy technologies will provide significant environmental relief. And ultimately, these findings prove that the sustainability of macroalgae bioethanol is not just a question of feedstock availability or a single technology choice. Instead, it is a matter of comprehensive energy and systemic design. Thank you very much for your attention, and I'm now open to questions.
I have a question,
Yeah,
but also I see from user Haralabos Kamilatos a question, which is the smallest installation size of the third scenario?
let me
Yes.
give me a second. You can see my screen, I think. or no? Can you see my screen?
Yes.
Yeah. Yes,
Okay.
Yes, yes.
Well, I'm not quite sure about the. Let me just look again. Yeah, it doesn't work this way. I'm not quite sure. I didn't study about the smallest installation size of the third scenario, so I'm not quite sure what the size into a room. I don't quite get the question, to be completely honest. Into a building.
The
I
question is
think
simple.
about the area size, yeah. The square meters, or if
I haven't
you have this
studied.
information available. Mm.
No, 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 no. It was just a scenario. I didn't analyze it furthermore about the
Mhm,
size.
mhm,
So just a question. I consider that your assumptions is not for a lab application, but this is, let's say, a pilot to commercial, let's say TRL 6 to 8. So the size, if this is the answer, is that this application is considered as at industrial scale.
Yeah,
Yes,
for a
yes, right.
biorefinery, I think.
Bravo. This is what it's. So this is very important point because during this was very good question because during these seminars we see and we present the problem of scaling up of what we do. But in your study, I consider, and it was more really, let's say, real scale application and not just an application in the lab. So
Correct. Yeah.
this is part of the answer. So from this basis, you can build on that. I have several scenario. We can make also techno-economic analysis or whatever you want. So my question is very relevant, but it was more basic, and maybe it's important to because what we do is to train to other researchers like you in your age or your maybe to give them some approaches useful to develop their own work. So the question is. We have seen the scenario, the different scenario, three scenario, could be 4, 5, 6, 7, or whatever it is. But let's go back. How have selected the scenario? If you would like to give us some idea how we decided to select this scenario
Yeah,
and
yeah.
not other one. Yes, thank you.
Firstly, I would like to say that I chose to study the stages of pretreatment, chemical pretreatment at hydrolysis, and I didn't study distillation and dehydration, since they are considered the most energy intensive, because they are mandatory stages for bioethanol production. I mean, the pretreatment and hydrolysis. So I chose to study the effect that other stages have with more alternatives. Now for the scenarios, optimization scenarios that I chose for scenario one uh, to replace the energy with photovoltaic, scenario two with solar thermal, I think that these choices were because these technologies are the most, I think, viral in 2026. We hear every day replacement with solar thermal, with photovoltaic. So I wanted to show basically that they are two basic applications, but they have major. Give me a second. Excuse me. Um, Give me a second to find the word because I'm really nervous.
No, it's okay. Your answer is good. I mean, you talk about the maturity of the technology and the
Yes, and they have I can't even find the word in Greek. Uh, I'm sorry, I can't find the word even
They're,
in Greek.
they
Yeah,
they are used broadly, these technologies, no?
yeah, but they
If you,
have consequences. They have
ah,
consequences. So we have to take in mind that they are technologies that we use every day, but they have bad consequences.
negative, you mean negative.
Negative, yeah.
So, for me, it's okay. It's okay. I think you answer very well. I think the people can think about it. It's fine.
Yeah.
So there's another
Uh,
question about the infrastructure.
on yours, do you deal
Ha-
How in your LCA do you deal with the fact that equipment that burdens, for example, your process ecotoxicity can be used multiple times? Meaning doesn't repeated use of the same equipment reduce the actual burden per production run? I I'm not sure about the life cycle, the age that the equipment have. I mean, I'm not sure how many years can I use it in an industrial scale that works every day so I can run it, so I can use it multiple times.
Sorry. I think that the system behind LCA gives you some normalization, takes into account the lifetime for normal use, so allocates also the impact from the use of the infrastructure. So for sure, as for photovoltaics, you have took it into account, yes? Okay. And you do have any comment?
I'm sorry, my connection, I didn't hear you what you said, the last one.
I mean that
Yeah.
LCA
Mm-hmm.
is following an ISO,
Mm-hmm.
so it normalizes this number, this impact. So the system itself gives you the answer, so takes into account this kind of problems as concerns the how many years the infrastructure is used, etc., etc.
Yeah, that's true, but I didn't analyze furthermore about the normalization, to be honest. Um So I'm not quite sure how to answer this question.
Okay, so it's okay. So
I
that's fine.
think yeah, but the same equipment possibly reduce the actual burden per that production run. I mean, it's logically yes, logically yes.
Yes. So I mean that the way you have seen that photovoltaic has an impact to the construction, not to the operation. The same also was with the same infrastructure in your calculations. And the main
Yes.
finding, as you already explained, was to see how, let's say, neutral technologies can have a really impact at the end because we have to take into account their environmental impact assessment. Okay. Thank you very much. I think, yes, thank you. Thank you. It was her first presentation after her diploma thesis, so I have to congratulate her. Thank you, Tania. Perfect
Thank
presentation.
you.